Hey everyone, and welcome to today's Explainer. I am incredibly excited to unpack a seriously fascinating piece of software engineering with you all today. We're going to completely demystify the complex architecture running behind the scenes of the VS Code B4X IDE Companion. If you've ever stopped and wondered how modern code editors just seem to magically understand your code, giving you instant completions and catching your typos before you even hit save, you are absolutely going to love this. We're diving into a research paper that maps out a highly sophisticated language server protocol, or LSP, implementation that literally revolutionizes B4X development by bringing this deep semantic intelligence right into the editor.
Okay, let's dive into this. The core problem facing developers of niche programming languages is, well, the tooling. Mainstream languages, think Python or TypeScript, they have massive corporate backing for their IDE tools. But what if you're working with a powerful yet niche rapid application development language? How do you build a robust language server entirely from scratch that can handle deep code intelligence without just buckling under the pressure? The solution documented here is an absolute masterclass in system design.
So here is our architectural blueprint for today's explainer. First, the B4X IntelliSense challenge. Second, the dual indexing revolution. Third, client, the deep thinker. Fourth, server, the fast indexer. And finally, number 5, bulletproof system resilience. Let's start right off with Section 1, the B4X IntelliSense challenge. So B4X is a family of rapid application development tools. You've got B4A for Android, B4I for iOS, B4J for desktop, and B4R for Arduino. And honestly, building an extension for this entire ecosystem is a unique nightmare of edge cases. First and foremost, you have strict platform isolation. Meaning, if you have a B4A Android project open, it must never, ever see a B4I iOS library, even if they're installed on the exact same machine. Then you're dealing with multiple library formats to parse: XML files, zipped .b4xlib archives, plain source modules. Add in heavy type inference requirements and the fact that the tool literally has to dynamically discover installation paths by digging through the Windows registry. Yeah, you've got a massive engineering hurdle on your hands. To handle all this potential chaos, the architecture leans on one fundamental mantra: nothing is assumed, everything is factual. In practice, this means the codebase is fiercely defensive. I mean, every single file path is strictly validated on the disk before loading. Only libraries that are explicitly declared in the project file's configurations are actually loaded. There is zero guessing. And doing it this way completely prevents entire categories of cross-platform contamination bugs from ever seeing the light of day. Moving right along to Section 2, the dual indexing revolution. Now, what's really interesting about this slide is how they solved the processing problem. Instead of trying to force one giant program to do everything, this architecture essentially splits the brain right in half. On one side, you have the client, running inside the VS Code extension host, using TypeScript. This is the deep thinker. It performs deep semantic parsing. It understands full method signatures and does exact lookups. Then, running over in a completely separate Node.js process, you have the server. The server does shallow parsing. It really doesn't care about the deep logic. It just cares about finding symbol names instantly using really fast prefix lookups. They operate independently, and together, they cover the whole shebang. Every IntelliSense need perfectly.
Which brings us to Section 3, Client, the deep thinker.
So the client powers something called the type inference engine, which is what enables complex dot completion. Think about it. Imagine you type btn.text.length into your code. How does the editor actually know what .length is? Well, it happens in 3 brilliant phases. First, local variable collection. The engine scans your code and sees, okay, btn was declared as a button. Second, expression resolution. It looks up the button class, checks its properties, and sees that .text returns a string. Finally, owner class inference. It looks at the string class to confidently suggest .length, which it knows returns an int. It chains all this logic together completely seamlessly in the background.
And because the client has such a profound semantic understanding of your code, it can provide incredibly powerful diagnostics. It catches misplaced type declarations. It validates call substring references. So if you rename a subroutine but accidentally forget to update the string reference calling it somewhere else, the client is going to throw a warning. It even features this really complex exclusion logic to detect unused subroutines and unused B4X libraries, all while carefully ignoring things like event handlers and lifecycle events so it doesn't bother you with false positives. It's honestly like having a senior developer reviewing your code in real time.
All right, let's jump into Section 4, Server, the fast indexer.
So, the crucial point here is exactly how the server achieves its blazing speed. It relies on a tree data structure. Now, a tree is essentially a tree where each node represents a single character. If you type B, then U, the server just walks down the B branch, then the U branch, and instantly finds all symbols starting with B, like button or buffer reader. This enables what computer scientists call big O of prefix length lookups. But in plain English, it just means no more staring at a loading spinner when you want a completion menu to pop up. Lookups are basically instantaneous no matter how massive your project gets.
Now that tree is just one piece of the global symbol table. This table brilliantly organizes data to power cross-file features. You have a by-name map for exact instant name lookups, like when you command-click to go to definition. You have the tree for that prefix-based completion we just talked about. And then you have underscore symbol store and underscore file to IDs maps. Working together, these allow the server to do incredibly sophisticated tasks, like project-wide case-preserving renames. Say you change a variable from an uppercase myvar to newvar. The server finds every single instance across every file, safely ignoring quoted strings and comments, by the way, and updates it while preserving your exact casing.
And to index all these files, the server uses parallel worker threads. But look at this number right here. 2. Just 2. The architecture strictly caps parallel worker threads at a maximum of 2. Why? Well, language servers run in the background while you are actively trying to use your computer. Capping that concurrency at 2 keeps memory usage incredibly low. It prevents the extension from hogging all your RAM while still parsing files rapidly enough that you literally never notice a delay. It's just a perfect balance of high performance and resource respect.
Which brings us to our final section, Section 5, Bulletproof System Resilience.
Look, software breaks, files get corrupted, environments get locked down. But this system is fundamentally designed to survive. It features aggressive, graceful degradation. If a specific file crashes a worker thread, bam, that file is immediately blacklisted so the rest of the project can keep indexing. If VS Code is running in a restricted sandbox mode that completely blocks new processes, the extension detects it and just falls back to a single-threaded, degraded mode instead of crashing. If a platform is missing, it skips it silently. If the server process dies completely, there's a strict restart budget. It'll try to recover up to 5 times before gracefully giving up. It is incredibly rugged.
And this brilliantly illustrates the user-first mindset of this entire architecture, snapshot persistence. When you close your project, the server takes its entire global symbol table and dumps it into a simple, lightweight .b4x-index.json file. The next time you open the project, it loads that JSON file immediately. This means you get absolute zero wait time on startup. You have instant basic IntelliSense from the literal moment the editor opens, while the server quietly re-verifies everything in the background.
So we've seen how splitting the grain into a deep-thinking client and a lightning-fast server solves the absolute hardest problems in language tooling. And we've seen how defensive coding and graceful degradation create just an unbreakable user experience. So I'll leave you with this final provocative thought to chew on. Should this dual indexing, highly defensive architecture become the standard blueprint for all niche language tooling moving forward? It definitely makes a compelling case for revolutionizing how we write B4X. Thank you so much for joining me on this deep dive today. Keep learning, keep exploring, and I'll catch you in the next explainer.